One thing missing. How to do that? Ah, is it this?
Yeah.
I think someone was experimenting earlier about. Okay. Right.
All right, everyone. Let's get started. This is our first science session, so this is very exciting, and we start with very distant things. So our first speaker is Emma Curtis Lake, speaking on the first results from the JADES, NearCam, and NearSpec survey. So take it away. Thank you.
Thank you. Hi, everyone. Thank you so much. I just want to put on my timer. Thank you so much for the opportunity of speaking here. It's such an exciting conference to be a part of. As said, I'm presenting first results from the joint NearCam NearSpec GTO survey called JADES, but I'm mostly concentrating on the NearSpec side. And some of you might know we've had some exciting results. It's a huge team. This is by no means a complete list. In fact, this is just sort of like the co-authors on the first NearSpec paper, and I've highlighted in orange either people that are here, Stefan is over there, or people who are speaking later today. But to set the scene, we're looking at sort of the early universe. So right after the Big Bang and stuff has gone on, we've had rapid inflation, and it takes some time for things to cool down, and we get neutral hydrogen and helium condensing out of that soup of charged particles. And we have kind of a boring epoch called the Dark Ages, where not very much is happening, right? And it takes some time for gravity to do its work for some regions to get dense enough to ignite hydrogen fusion and give us our very first population of stars. So we call them population 3 stars, and they're just built from pristine hydrogen and helium. And at that point, we have energetic photons in our universe that can escape from the galaxies, the stars, and ionize the intervening neutral hydrogen in the surrounding medium. And we go through a process over about the next roughly billion years at which most of the hydrogen in the intergalactic medium is ionized, and we call that very grandly the epoch of reionization. And most of the results I'm going to show you are from sort of this sort of epoch onwards. What's happening in the galaxy population as a whole, we have measurements of the cosmic star formation rate density, where we see a sort of rapid buildup, and the exact precise form at early times is kind of being figured out right now. And this is really the buildup of the galaxy population from the very beginnings. And then we get to a peak at around halfway through cosmic time, and then the epoch of quiescence takes over, and either galaxies have run out of gas, or maybe black holes have heated things up and stopped things from falling in. We don't care about that stage for this talk. We're looking at the first half of the history of the universe. And thanks to this glorious telescope, we're now getting spectra, rest frame optical spectra for a large portion of it, and then losing some of the rest frame optical for hundreds of galaxies at once with the incredibly sensitive NearSpec. Of course, there are many different spectroscopic modes. I'm concentrating on the MOS mode from NearSpec in this talk. So for our survey, we are visiting 2 regions of sky that Hubble knows very well. This is good south, and here is the Hubble ultra-deep field with the deepest Hubble imaging, and this is good north with another nice deep patch of imaging here for Hubble. And we want these patches of sky because when we're looking for the highest Redshift galaxies, we want to make sure that we don't see them in Hubble, because actually that neutral hydrogen gets in the way. We shouldn't see light from them. So the deep Hubble imaging helps us with that. It also helps us with getting better photometric redshift, etc., for all the rest of our prioritization. Now, these are sort of pre-22 slides. It was sort of possible layouts, and it all looks a little bit messy and complicated, but it's not. At its core, it's simple. The idea is NearCam imaging with NearSpec follow-up. And it just gets complicated because we want to use this observatory efficiently and take other modes in parallel. So in terms of what we're trying to put together for a spectroscopic sample, this is a very simple graphic to show it, and the axis kind of extends way off here. It goes much further. We want to sort of get all the cool, fancy galaxies around here. We don't really matter if it's a mass-selected sample or star formation rate-selected sample. We want to find them, get spectra of them. But we also want to build up a beautiful statistical sample, approximately mass-selected from around redshift 1.5 to 2.5. So this would be our statistical sample of around 2,000 galaxies. That's what we're aiming for. So good north, we haven't started that yet. This is an old layout. I'm not really going to talk about it. Good south, however, and we've got going on the survey. So here's some NearCam imaging. I'm not going to tell you much about this. You can hear Brandt's talk later today. But we've covered sort of a deeper imaging here and slightly less deep imaging there. And when NearCam was building its mosaic down here, we had NearSpec go in and take spectroscopy of Hubble-selected galaxies, so using the parallel modes, relatively shallow spectra. But somewhat more exciting, we've also had our first deep pointing. So this was pretty much centered on the Hubble ultra-deep field, which you can kind of see by the extra density of targets here. We've had up to 28 hours in R of 100, up to 9 hours in each of the 3 R1000 gratings to cover the full wavelength range, and then we have one R of 2700 grating up to 9 hours. And we've been selecting our targets with the EMPT, and just to advertise that that's been released on GitHub if you want to check it out. And we're really getting some beautiful spectra out. So these are from the Prism. Unsurprisingly, 28 hours is giving us some beautiful spectra. We have some great stonking continuum here, and then some really bright emission lines. We've got H alpha, O3, H beta. Doesn't take us long to lose H alpha. It's gone off the end there. It actually doesn't take us too long to lose all of the strong lines. We've got some of the UV lines here as well poking in, even at the low resolution part of the grating. But before we lose those strong lines at the very highest redshifts, we're able to do some diagnostics of them. This is work by Alex Cameron in preparation. So you can see the purple dots here are from our galaxies. The gray sample is from Sloan, so local galaxies. So they're not inhabiting quite the same spaces. We've got some nebular emission modeling on here at constant ionization parameters, so going up to higher sort of ionizing power. And also from high to low metallicities. So we've got low metallicity galaxies, ionization parameters completely expected. And also currently these line ratios, none of them are sort of unprecedented. They're somewhat similar to some low redshift analogs. Another very exciting science case to come out is looking at not quite baby black holes, but almost baby black holes. So here we have some very thin forbidden lines. And then we have a broad component to H alpha here from a black hole. You see it here, and you see it very clearly in the 2D, which is really nice. This is at Redshift 5.9. And so we're really pushing the black hole galaxy mass relation to much lower masses, building up an understanding of the population of black holes at this epoch. And then onto the final one, which you may have heard of, we've also managed to get some spectra of some very high redshift galaxies. So these are 4 of our highest redshift galaxies that we put on shutters, all above redshift 10, and they all came back with a positive spectroscopic confirmation. So we had, on Friday, NASA blog and ESA blog went up, which was pretty exciting, and over the weekend it has been picked up as a story in various places. BBC, Jonathan Amos, a really nice write-up. Some love for wonderful co-I, Stefano Carniani in Pisa. Some blogs have picked it up, and also New Scientist. That's been quite fun. But back to the science, here's a different view of those spectra, which I think maybe is more useful to people here. So you can see the 2D, you can see what we're looking for is that we really get no flux shortward of 12, 15 angstroms because we have neutral hydrogen in the way. And we get good continuum measurements. And other than that, they're somewhat featureless. Just to give you some context of these galaxies, here's the previous highest redshift spectroscopically confirmed galaxy, GNZ11, and I'll just say a short apology to Pascal because I managed to put the paper up without the reference in there, and that will be rectified shortly because, of course, this is what we're comparing to, so just an apology there. But here we go with this one. One here, 11.58. This was a cool one. This was originally found by Richard Bowens in about 2010. Found it again, well, didn't find it again, looked at it again in the UDF-12 imaging, found that it was only in one band. It was either super low redshift, well, not super low redshift, intermediate redshift, mask rating as high redshift or high redshift. So now we can confirm it was actually the highest redshift object that we were seeing in HST imaging. One here, 12.63, one at 13.2. So these are new. These are from NearCam imaging alone that were identified. Kevin Hainline, Dan Stark, Ryan Ensley were very key in finding these for us. And as I said, the spectra are fairly featureless. We were a little bit disappointed to begin with. We were hoping to see some rest frame UV lines until we started full spectral fitting. So there's a lot of parameters here. I'm not expecting you to sort of look at them in detail. I'm just going to pull out this one row for you and put on some markers to guide your eye. This is 10% solar. So we have our 1 sigma, 2 sigma, 3 sigma limits. We're comfortably below 10% solar metallicity. And here's 5% solar. So once we get down to these low metallicities, you can see that there are hints of lines in the model spectra. It's just that we wouldn't be seeing them at this signal to noise ratio. And then again for the other 2 objects and the 2 lines there. So where we get lower signal to noise, not quite such firm constraints on the metallicity, but still very low. And even with those low metallicities, we look to the UV slopes because often UV slopes have been used to try and find some really extreme populations. And often people were looking sort of down here to look for very extreme galaxies. These seem to have really extremely low metallicities, but are not extreme UV slopes, likely because of the nebular continuum making them redder. So I could talk a lot more about these guys, but I'm kind of running out of time, so I'm going to leave you with a nice summary of some of these results I presented. So at redshift 6 to 9, the emission lines reveal low metallicities, high ionization parameters. NearSpec is revealing small black holes in the early universe. And we have 3 galaxies with spectroscopic redshifts higher than previous record holders. And the featureless continuum is revealing very low metallicities. So thank you very much. I look forward to your questions.
All right, we have time for some questions. Maybe we should first check if there are any online. Not yet. Okay, so we can take them in the room. Okay.
Well, thank you, Emma. That was just fantastic. It's just amazing to see these spectra. So my question was really about the lack of emission lines. I mean, it's really surprising that even at 5%, I mean, you would have expected at least C3 and, if C3 is, too ionized, then at least the C4 lines. So I was just curious about which models you were comparing them to.
So we're using the nebula emission modeling from Gutkin with updated stellar emission models. And we do compare to low redshift analogs in the literature, right? And our 2 sigma upper limits. It's only really in this galaxy where it's significantly below what we might see. And actually those ones are around 10% solar. And we're dominated by the lowest ages in the galaxy. So I think actually when we compare to local analogs, we're quite consistent with the low metallicities with the limits we have.
So you think it's the actual elemental abundances are so low that that's why you don't see those lines?
Yeah.
Hi, Natalie Willett, University of Montreal. Really, really interesting talk. My question was about the stellar mass to black hole mass plot. Obviously, it's a small number statistics still, but I noticed that all 3 are above the line. So do you have any idea, or have you started considering that perhaps this is not a linear relation? There's a turnoff, and what would be causing that at higher redshift?
That's an awesome question. I would say ask after Hannah Ubler's talk this afternoon, because she's going to go into more details. She's been thinking about this more than I have, and she'll be a better person to answer it.
Thank you.
All right. I think we have to move on. Good thing we're all here, so we can talk afterwards. Yeah, great. So our next speaker is Rachel Bessenson.
Perfect.
Right, and she'll talk on the Uncover Treasury Program, Ultra Deep Early JWST Community.
Great. First of all, let me just say what a pleasure it is to be back in this auditorium. Really, and on this occasion, I just couldn't be more pleased to be here. The other thing that I wanted to say before I start launching and talking about this JWST Treasury program that I've been working on is that in contrast perhaps to Emma's beautiful talk, this is going to be a little bit light on science results and rich on beautiful pictures and promise. And you'll see why in a second. Does this work? I have to start with the people that I've been working with, and in particular, I'm going to try to highlight the work of the more junior folks on the second row who have really been making this, the gears turn over the last few months and really over the last 3 weeks since we finished getting the first act of our data. So Uncover is a tortured acronym. Please don't get on my case that it's not actually Uncover. I can't uncapitalize NearCam and NearSpec. But Uncover is in a very well-studied field. Abel 2744. There's a little box here, and I'm highlighting it for a reason. People, especially who are familiar with HST observations from the Hubble Frontier Field program are very familiar with this cluster. But this is the cluster that was focused on with the Abel 2744 Frontier Field imaging. But the Abel 2744 cluster is sometimes nicknamed the Pandoras Cluster. It's actually a composite of many different clumps with 3 primary clumps. And so our NearCam Mosaic is meant to map this whole thing So just to give you a kind of idea, on the left you can see an old, and by old I just mean HST and ground-based imaging based map of the frontier field cluster. The frontier field cluster is this little dotted box there. Our mosaic, our NearCam mosaic, kind of fills this entire factor of 2 magnification curve. And Abel 2744, just to give you an idea, in blue, it has been hammered to death with HST, although you'll notice that actually it doesn't extend as the HST imaging doesn't extend as much into this northwest corner. There are a number of other JWST programs in this field. This is one of the fields that JWST is going to be studying, kind of really in a multitude of different ways. And this is just the Uncover program is just one of them. Okay. So I wanted to kind of add this caveat. We also have a near-spec component. That's Act 2. I'll refer to as Act 2 or Epoch 2 of our program. I'll come back to that, but this is just kind of a cartoon placement. So in November of 2022, Act 1 of Uncover started. It was actually technically supposed to start on Halloween of 2022. And it's an ultra-deep NearCam mosaic that fills this wide footprint of the Abel 2744 cluster. Simultaneously, we get NEAR's parallel imaging. I actually won't show these mosaics, but I will show you how to look at them. I'm going to focus on the NearCam primary mosaic. It's super deep. So just so that you can kind of get a sense, here's the Uncover program in depth versus area with respect to other, I mean, everything on this plot is ridiculously deep, but Uncover is one of the deepest programs, not the deepest program, one of the deepest programs, but it's also, it's a treasury program. The data are public from day one, and as I'll emphasize later, our reduced mosaics are available to the community now. So super deep, 30th magnitude. When you take into account that this is a field with regions of really extreme gravitational lensing, that kind of boosts you into the regime where, you kind of probe less area, but you get kind of some intrinsically faintest sources. We have lots of different filters. You can see on the left, there's HST imaging in much of the field, but not all of the field. We have 7 filters with our NearCam and fewer with NIRAS. The NIRAS imaging is like comically deep. We actually were worried that we had made a mistake in our calibrations, but no, it's beautiful. That was really like a stressful 24 hours. Anyway, so a lot of the work, the productivity of our team has been wrangled by our survey manager, Sedona Price, who's a postdoc at the University of Pittsburgh with me. That is a real-time picture of her. Actually, it's sped up, maybe. But without the time zone issue. Anyway, so Sedona in particular, I'm highlighting here, has put together a beautiful website. And if you are interested in even just like playing around with some of the images that I show, I'll put that QR code at the end. Again, go to our website. You can download our three color mosaics and scroll but don't do it before you have something to do, because you have a lot of time doing it. So the one thing that I wanted to say is that on October 31st, Halloween, I woke up like super excited for a treat, and instead got a little bit of a trick. So if you have eagle eyes, you'll see that the footprint of our NearCam mosaic is a little bit wonky. The position angle is a little bit off. And that is because our first visit failed GuideStar acquisition. And again, a huge thanks to everybody and at the Institute who made it possible to kind of replace that with, a slightly different position angle. But, as my colleague, Andrew Zettner, likes to say all the time, you cannot let perfect get in the way of good. And in this case, amazing. Okay. So, our first visit was repeated. There's a slightly different position angle, but if you ever look at our mosaics and wonder what happened, that's what happened. So we are in the process of creating internal and then publicly released data products, higher level data products. And one of those is Photometric Catalog, so modeling the BCG light, the ICL light. This has been being led primarily by John Weaver. The Photometric Catalogs are basically primarily being run by John Weaver, throwing out the beautiful low redshift cluster galaxies. Detecting sources in these images. By the way, these mosaics also include all JWST imaging, so JWST imaging from the GLASS program and another DDT program in the field. These are comically deep. So here's kind of a weight map of depth as a function of position in the field, and some catalog depths. The catalog depths come from larger apertures. That's why there's a slight difference. We have a new updated lensing model that's also available publicly on the archive. In particular, it highlights this this new clump in the cluster, where there are 75 newly uncovered multiple images in this beautiful part of the cluster. And we're modeling, we've figured out how to make Prospector a faster hammer, to use Prospector as a photometric redshift and a stellar population machine on these big, huge data set with, tens of thousands of sources. And I just wanted to kind of, before wrapping up, show you some beautiful images and zoom in a little bit. So, in our mosaic, you can see beautiful images of galaxies getting ripped apart in the cluster. Falling in, ram pressure stripping, pods getting caught by our NearCam filters. Unbelievable lensed background galaxies in the well-studied part of the cluster and in the new part of the cluster. Let me just embiggen for a second. I'm like, maybe one more time. Okay, these data are an unbelievable treasure trove. I cannot tell you what the most exciting thing in here is yet, but there's some cool stuff, and I really encourage you to download them and take a look. And this is just zooming out on the new clump. Here's the, we knew that there were galaxies that HST was blind to. We, of course, find them with JWST. So here's an ALMA source that was invisible in even the very deep HST imaging that existed in this field. So the exciting thing, and this is just another way of seeing the overview. So what I wanted to say is that the exciting thing this is just Act 1 of Uncover. This is a simulation of my office for the next 8 months, and sometime probably in July, although the scheduling is still a little bit up in the air, we're going to come back and get near spec MOS Prism spectra, and those will range. We'll kind of create 7 overlapping independent near MSA designs, and get from 2.7 to 19 hours. Per source, something like 500 objects. So in the paper and on this plot, there's just kind of one representative pointing, but this is going to be required to figure out exactly what to do. And at the same time, we'll get another ultra deep NearCam parallel mosaic, which is exciting in its own right, even though it's outside of the, the kind of lensing part of the cluster. We'll get 2 instead of 1 medium band filters with NearCam. Super excited about that too. And then you can simulate and get really excited about the different types of things that we'll be able to get beautiful Prism spectra for. And there's more detail about this in the paper. I just wanted to wrap up and say the paper has some details about what our planned survey releases are, and I'll leave this on the bottom and just stop with this kind of parting thank you. I know that there was an incredible amount of work that went in to getting us to the point of making these images, and so thank you to everybody who was involved in every stage of the way and continues to make these work.
time for a couple of questions. Anything online? No. All right. In the room? Oh, there's a question.
One quick question from online. Have you seen any new physics?
Probably. No, I don't have no idea.
Right. Any questions in the room? Got one in the back.
Just a very simple question. The 6-hour-ish exposure is only referring to the 2 middle stripes, right? When you have the overlap of modules?
It's 6 hours. No, I think it's twice that in the stripes, in the deep stripes.
Right. Okay, thank you.
Yeah.
So I actually have a question as well. So in the SMAX field, in the cluster itself, we see,
yes,
we see globular clusters, these amazing population. And it looks like you have the same here, but I wasn't sure.
Yeah, I think almost certainly you can see it.
I have some incredible statistics on that. All right, any other questions? Oh, there we go. Claudia.
I was wondering if you haven't really said much on how you're going to select the spectroscopic target for the follow-up. Is it more high redshift? What's your plan?
So we have a priority list, and we'll start with things that are the most rare, so the most distant galaxies, that kind of thing. And those will probably be the faintest, although it depends on how magnified they are. And then we'll kind of go down the list of low mass, reionization era galaxies, quiescent galaxies at the highest quiescent galaxy candidates at the highest redshifts, super dusty galaxies at the highest redshifts. But it's going to be a bit of a juggle, I think, is the answer. Called priority list, at least in the survey paper. Yeah.
All right, let's thank our speaker again. Steve Finkelstein on the Sears survey.
Thanks, Klaus.
So, yeah, take it away.
All right, thank you. Thanks for allowing me to be here to tell us about our survey. And I will start with a big thank you to everyone in the mission that has made this amazing observatory possible to take these amazing data, including this image shown here, which is not from Sears, so not trying to take credit for this. I'm going to talk about the Cosmic Evolution Early Release Science Survey. And I'm going to show you some results, but this is all the result of a huge team of about 150 people. And you can go to our website, sears.github.io, learn all about our program, our data release, and our people. And we also have a Twitter handle that is moderately active these days. So start with the tiniest bit of motivation. I don't need to spend too much time here because Emma did such a wonderful job. Again, this is one way to look at the history of the universe, the evolution of the cosmic star formation rate density, and we broadly see that from early times the universe grows more and more stars, and then there's some peak, and then things kind of turn over as the universe is sort of dying off, or star formation in the universe is dying off. And there's a lot of data on here, but we can sort of put it into sort of two categories. A lot of agreement here. There we go. Lots of agreement here, and sort of less agreement out at high redshifts. And now this isn't unexpected because when you're looking at redshifts greater than 10 in the pre-JWST era, you're finding galaxies in usually one filter, at most two filters. So you can imagine the selection of such sources is very difficult, but of course that motivates a wonderful new space observatory to probe this early time. And so to move to redshifts greater than 8 or really greater than 10, we need something like JWST. Here is the full-scale model of JWST, and what I'm being told is Austin, Texas. If you've been there lately, it looks nothing like this anymore. There's about 20 new skyscrapers behind this field. But we had the pleasure of seeing the full-scale model there back at South by Southwest. And at that time, we already sort of knew what we wanted to do with this telescope. We knew we needed deeper imaging, we needed redder imaging to be able to study this early universe. And we also know that we needed spectroscopy to confirm the redshifts, to study the ionizing conditions, to search for forming black holes. And so all of these cases led to our proposal for SEERS, our early release science program, that is now in progress, which is really exciting. And I'm very glad to be here to share it with you. So some of the science goals behind SEERS, and all of these figures are actually circa 2017 proposal figures. We haven't changed them. Been too busy with real data to do that. The way we planned out SEERS was around a base NearCam Mosaic, and I'll show that to you in a second. But our primary science goal was to study the Redshift 10 universe, and that sort of decision trickled down into all of our decisions. And so what we set up was a 100 square arc minute 10 pointing NearCam Mosaic, and based on the simulations at the time, 5 years ago, we thought that SEERS should detect sort of between 5 and 50 galaxies at redshifts greater than 10. And that should allow us to distinguish between models that have different star formation history assumptions or different star formation physics. And this is just a figure from the proposal showing some of these different models, but I'm going to sort of boil it down to a single number, and that if some of the more optimistic models are correct, which would mean that the star formation rate history that I showed on the previous slide had a sort of smooth decline out to earlier times, SEERS should find galaxies at redshift 12 and maybe beyond. And if some of the more pessimistic models are correct, we really should sort of max out at redshift 11 and maybe be lucky to find a few there and not much beyond that. For our near-spec observations, we want to do many things, including searching for some of the earliest growing supermassive black holes. And there's a poster by UT graduate student Junyong Jian on this topic, and studying metallicities of galaxies, studying ionizing conditions of galaxies, things that we've already heard about. Again, this is a simulated spectrum. We get our real spectra next week or maybe the week after. So we'll have to stay tuned for that. And then the exquisite resolution of JWST is really going to allow us to study the structure formation at a variety of redshifts. So I'll tell you a bit about the SEERS observing plan. So we're observing with several JWST modes, and we really looked at ourselves as sort of the blank field parallel survey test bed for JWST studies. And so this is our NearCam Mosaic, and this is from our latest APT with this sort of fancy graphic made by Dale Kuchevsky showing our 10 NearCam pointings. And this is taking place in the EGS field. This is a well-studied field from Hubble, part of the Candle survey. And so we have the Hubble imaging in place. The grayscale shows the Hubble field of view or the Hubble layout. And here are 10 NearCam pointings. The crosshatch regions are where we're doing NearCam wide field slitless spectroscopy. That data will also come in here in the next few weeks. In parallel, we will be doing 8 MIRI pointings. We can see the field of view with MIRI is smaller, so we're not covering the whole field. Some of these fields, half of them were focusing in the 2 bluest MIRI bands to go as deep as possible to study stellar mass and high redshift galaxies, and the other 4 were using almost the entire filter set to study dust emission at lower redshift. And then this is where our near-spec pointings will fall. We have 6 near-spec pointings. We're doing R of 100 Prism and R of 1000 medium resolution grading in all of these. And based on our final, version 3 final APT file, we should get over 1,000 sources, independent sources in slits. So lots and lots of spectroscopy to come, including in this pointing, which we were allowed to move. This was over here, and we moved it here because there is now NearCam imaging already, and we were able to put slits on JWST identified sources, which was not actually part of the original plan, because originally we were supposed to do SEERS all in one go. And when the telescope launched, we thought we might get all of our data in June, but as commissioning was sort of doing its thing, they didn't start Cycle 1 Science early enough to get all of our data in June. Fortunately, we were able to get some in June. And so this is the data that we actually have in hand now. We have 4 NearCam pointings in hand now, 4 parallel pointings in hand now. That took place in June. And then what's going to happen sometime between December 17th and December 28th, they told me we might find out tomorrow what day it's going to be, or days, is about 50 hours of data, basically the entire rest of the program. All of our near-spec, all of our NearCam GRISM, and 4 remaining MIRI parallels. And so when we put it all together, this is what the final SEERS survey will look like here in just a couple of weeks. So we have data. What does it look like? This is our mosaic, our press release image from our June 2022 observations. So again, 4 NearCam pointings here, all in the EGS field. And one of the things we did that week, we had a group of us working in Austin. We took this to the Texas Advanced Computing Center VisLab, which is this big, huge 50-foot wall. And we put this image up there, or a proto version of this image up there. And the resolution is just amazing. So at that time, we picked out sort of these 6 galaxies to call out in this image at the bottom. And what's amazing to me, this is not the science I do. these are, Redshift, I don't know, 0.51 something galaxies. You can pick out the individual star clusters by eye, and it really blew me away. And the other thing that blew me away that you could see by eye just in the days after having this is you would see these tiny, tiny, tiny little spiral galaxies that had to be Redshift 1 and beyond. And I'll show you one result about that. And you've already seen that from other papers in the literature, that disk galaxies are forming earlier than we had seen observationally. And it's really just due to the observational resolution limit of Hubble. And they're now popping out in JWST. And so just sort of on an emotional, visceral level, looking at these images are amazing. If you go to our website and click on blogs at the top, you can see this wonderful website that Rebecca Larson put together. You can download these images. This is the 3 megabyte version. There's a 400 megabyte version that you can download. Just prepare to block an afternoon of your schedule because you will spend a long time zooming around these images. And we're not the only show in town anymore. The Uncover images are beautiful. The Jades images are beautiful. There's a lot of fun you can have looking around. So this figure highlights one particular galaxy. This was a Redshift 9 candidate galaxy found with Hubble. You can see we don't see it in the bluer bands, and you can see the dropout. You do see it in WFC 3. This is like a pretty bright galaxy for Hubble. You can kind of see it there. It's like maybe barely visible in 50-hour deep Spitzer IRAC imaging. If you look really, really closely, this is what it looks like in Sears. This is in 2,900 seconds. So obviously this is way too bright to be looking at with JWST. It's about 26.5 magnitude, but it really shows the power of JWST. And you can see that actually the photo Z distribution before was kind of broad from 7 to 10, really peaks up now at a redshift of 8. So Redshift 9 candidate becomes Redshift 8 candidate. We'll get a spectrum of this galaxy here in a few days. Science is really beginning to flow. Many, many, many excellent papers from non-Sears team members. Of course, that's the purpose of this program. On our website, we're highlighting the papers written by team members. Anything with a red arrow, I'm going to try to talk about really quickly. And the one with the blue arrow, we're going to have a whole talk about from Jehan Kartaltepe here in a few minutes. So I'll start with our NearCam Data paper. So all of the science we've done, almost all of the science we've done has come from NearCam. And the ability of our team to do it was really based on the immense effort of Michaela Bagley, who's a postdoc working with us at UT Austin. And in Michaela's paper, they lay out a roadmap for reduction and analysis of any NearCam data. So if you have NearCam data, you want to learn how to do it, read Michaela's paper. We're working on a GitHub repository. It's not quite ready yet, but we'll have all of our codes up there. And just to briefly summarize the challenges we had to deal with, these data were taken in June, and so they were sort of dumped with everything on July 14th. We didn't have any previous experience to go on, right? So we had to deal with astrometric misalignment. Aligning each and every detector to one another was more challenging than we thought. Snowballs, that's fun. There's a fix now. Wisps, fix now. 1 over F noise, Michaela developed their own algorithm to do that. That code is also going to be on our website. Photometric calibration, which is a lot of fun. That is, I don't want to say fixed, but definitely a lot better than it was. And now we can make these beautiful mosaics. And so this is a summary figure from Michaela's paper showing both some short and long wavelength images of our field. So let's get to some science in my last 3 minutes. So our first science paper, of course, we wanted to look for early galaxies, and we had sort of planned to do this sort of longer-term holistic census, but as we looked on these data in the middle of July, one galaxy popped out at us. It was brighter than we thought we would see and higher redshift than we thought we would see. We happened to sort of decide that it was a really valid candidate and it was worth writing a paper on my daughter's birthday. And so this is Maisies Galaxy that we named after my daughter. You can see it's a bright little red dot right here. And we studied this in detail. We found that it was a galaxy at a redshift of 12, which already tells us something. The fact that we found 1 means maybe some of those pessimistic models are not describing the universe we live in. It's a very nice dropout that you can see the break is right towards the red edge of F150, which places it at a redshift of 12. And the exciting thing is if you look at a bunch of now modern era 2022 theoretical models, they basically don't predict we should have even found 1 in the 35 square arc minutes that we found. So now that's one galaxy. There's a big error bar on our data point here. So we spent the past few months looking for more, and we've learned that Maisie is not alone. We have about 26 candidate galaxies in our 4 pointings so far at redshifts greater than 8.5. This is a diagram showing magnitude versus redshift here. Maisie is the one with the little star here. A couple candidates at higher redshifts, including one up here, potentially to redshift of 16, first shown in a paper by Callum Donnan, University of Edinburgh. There's a color composite of all the candidates there and a couple results that we're finding. So we now had enough to make a luminosity function. And so this is a redshift 11 luminosity function, which is a little bit amazing to say those words out loud. Again, it's 35 square arc minutes, so our dynamic range is limited. Our data points are here, the darker red circles. And there's sort of one broad result I take away from this, which is that the blue lines show the evolution of the red stream UV luminosity function from 5 to 6 to 7 to 8 to 9 at the top of the gray curve. And if you just keep that going, the bottom of the gray curve is redshift 12. And you can see that the data points sit at the top. And so the evolution of the UV luminosity function appears to be slowing down. Now, there's a lot of caveats we could put in here. Small sample size, early days, photometric calibration. I don't really think the calibration is an issue here. Spectroscopic confirmation, we would love to confirm these, and I hope we will. But if this result holds true, it tells us that something is fundamentally changing in the way that galaxies are forming their stars at early times. Now, we could say, is any of this predicted by simulations? No, essentially. This is another look at our number of galaxies in these gray curves as a function of redshift, and a bunch of models, maybe too many models. And a few of them can kind of agree if you remove all dust and allow gas to instantly form stars from the second it's accreted. But broadly speaking, what we are seeing is an excess of that predicted by models. Not in any way that breaks the universe, online commentator, but in a really exciting way. And so in this Sears key paper 1, on page 40 or so, we go through a number of reasons that can explain this. And there are a lot, and I don't want to give too much preference, but one exciting scenario that at some point we should see in the universe is that you have extremely low metallicity stars where we think the initial mass function should be top-heavy. And if you look at theoretical predictions for those stellar populations, they should be more UV luminous. The ratio of UV luminosity to halo mass is higher by a factor of 2 to 4, which exactly explains this difference we're seeing here. So are we saying that's the case? Absolutely not. We need a lot more data. We need spectroscopic confirmation. But it's giving us a lot of hints that something really exciting is going on there. So I know that I am almost out of time, so I will give 10 seconds to a few other science results. Dale Kaczewski wrote a paper on some X-ray AGNs looking at their morphologies and their star formation properties and found that they all appeared to be quiescent, which is interesting. It's really correlating the timescales of AGN activity and quiescence. Pablo Perez Gonzalez looked at HST dark galaxies, so objects you don't see in the Hubble imaging, but you do see in the JWST imaging, and found that they essentially have 3 origins. Some are quiescent, some are dusty galaxies, some are extreme emission line galaxies. And then Kei Guo, a graduate student at UT Austin working with Sharda Jogi, looked for barred spiral galaxies at the excitingly high redshifts of redshift greater than 2 and found a few candidates. And that's just in our 4 pointing. So bars are forming fairly early in the universe. And so I will just leave out my take-home points here and take a question if I have time, and just point out again that round 2 of Sears, which is actually the majority of our program, 50 hours of data, is coming in essentially now. ERS program is public immediately. There will be 1,000 sources with spectra, and we look forward to seeing what we all find. Thank you.
All right, I think we have time for one question. Yeah, let's go ahead.
The intriguing result that the luminosity function suddenly stays, time invariant. But what was puzzling is the shape seems the same as well. That must constrain some solutions.
You mean the shape looking like a double power line?
Shape.
Yeah. I mean, so I think I haven't tried to model this precisely, but if you essentially keep the halo mass function has the same shape as well, presumably. If it keeps evolving downward, but the UV luminosities are evolving upward, I think you could get this slowing effect without changing the shape. But we're also, with what we're probing here, probing a very small, regime in luminosity. So we really can't constrain the shape yet. But I think the data is probably already in the archive, and if not by now, it will be by the summer to actually constrain the shape.
All right, thanks. Let's thank the speaker again. All right, so I think the next speaker is virtual, so I think we have to set that up, right? Sure.
So can I share the screen from my side?
All right, so so can you say something? See if we
yeah. Hello, can you hear me? Hello.
We can hear you.
Okay, cool. Can you see my slides?
Yeah. So make sure you enter full screen mode.
Yeah, I'm in the full screen mode now.
All right, great. All right. So our next speaker is Feige Wang, and who will tell us about the spectroscopic survey of biased halos in the reionization area. So yeah, please take it away.
Thank you. Thanks everyone for giving this opportunity to talk about the Aspire program. And also I wanted to take this opportunity to thank everyone who made the JWST possible to allow us to study the earliest supermassive black holes. So the Aspire program is a medium-sized program focused on the biased halos. It's different from the previous talks by others, but in this section, mostly focusing on the blank field. But this program mostly focusing on the supermassive black holes in the early universe, in the epoch of reionization. So the Aspire team is a relatively big team. We have about 60 collaborators now. And first of all, I wanted to start with the motivations of this program. So why we care about the supermassive black holes in the early universe. In the last 20 years, people have been trying to spend a lot of time to find the earliest supermassive black holes to understand when the first black holes appears and how they grew. So to date, people have found about 200 quasars above redshift 6, and with 60 of them at redshift beyond 6.5, and with the highest at redshift about 7.6. So the discovery of these quasars posed a significant challenge to the black hole growth history. And also, if you look at the density evolution of the quasars from low redshift to high redshift, the density evolution of quasars is very rapid. Like, for example, from redshift 7 to redshift 6, that's only a few hundred million years, but the quasar number density increased by a factor of 3, which indicates the black hole grew very rapidly in the early universe. And also, if you look at the black hole mass of these luminous quasars, they already host like a billion solar mass black holes. How those billion black holes, how those such massive black hole could form in such early universe, which is still open question, and we wanted to understand more about the earliest supermassive black holes. So towards a bigger size, like talk about the KPC size to see how about the host galaxy of these black holes. From the extensive studies with the ALMA by looking at the dust emission and the gas emission, people have found that those quasars are hosted by a galaxy with a very diverse morphology or kinematics. In the left panel, you can see like the first source with a clear the C+ velocity map, and which indicates the quasar host galaxy could be a rotating disk galaxy. But for the second one, there's no any velocity gradient, and it's dominated by the dispersion mode, by the random motion. And for the third one, you can see like the host galaxy is so some tidal disturbed structure, which indicates it could be a merger. And using those ALMA observations, the spatially resolved observations, we can already put some first order constraint on the quasar host galaxy dynamical mass and put it on the M sigma relation of the black hole mass versus the galaxy dynamical mass plot. And you can see that most of the Hazy quasars locates above the local relation, which indicates the black hole might grow earlier than their host galaxies. But from all these plots are based on the observations from the gas. Well, the gas kinematics is complicated, and people have never seen the stellar light from the quasar host galaxy in the early universe yet before JWST. And like in the right panel, we can see like this is the HST observations of some high redshift quasar, and there is no any detection of the quasar host galaxies. So that's a second point. We wanted to start high redshift quasar. We wanted to detect the stellar light from the quasar host galaxy and wanted to understand whether the black hole co-involves with the host galaxies. And to even a bigger scale, we wanted to understand how the black formed in the cosmology scale, like what's the dark matter halo mass, and what's the large scale environment of those quasars looks like. So from the simulation side, the earliest supermassive black holes, like a quasar with billion solar mass black holes, should form in the massive halos, in the most massive halos in the early universe. And those massive halos could be traced by galaxy overdensities. But from the observational perspective, currently there's no solid evidence about whether those quasars hosted by massive halos and inhibit large-scale galaxy overdensities. For example, in the past 10 years or almost 20 years, people have studied a lot of quasar fields using broadband imaging and also spectroscopy follow-up, but the results are inconclusive, and only few quasars were found in the galaxy overdensities in the last few years. So we wanted to understand statistically to study whether most of the massive black holes in the early universe reside in the massive dark matter halos and traced by the large-scale galaxy overdensities. So can we do all these three very different scales in the same program? The answer is yes with the JWST. So we can study the large-scale environment and the host dark matter halos of the earliest supermassive black hole. We can detect the quasar host galaxy stellar light, benefited by the high sensitivity and high resolution of JWST imaging. And also we can study the black hole itself by measuring the black hole mass by characterizing the aging feedback using the optical ionized emission lines from the quasar spectra. And also we can at the same time we can study the high-resolution galaxies in the quasar fields. So in this way, we designed the Aspire program, which is basically a legacy galaxy redshift survey in the quasar fields, and with the four main sense goals listed here. And in this talk, I will focus on the large-scale environment and the dark matter halos of the earliest supermassive black holes, and about the black hole host coevolution and aging feedback will be presented by Jin Yang on Wednesday. So our Aspire program aims to target 25 quasars at redshift between 6.5 and 6.8. We choose this narrow redshift range is because this is a sweet spot for the O3 doublet using the JWST NearCam slitless spectroscopy. And we have 65 hours, and we will cover about 280 square arc-minute for the spectroscopy at 3 to 4 microns. This is one of the largest spectroscopic survey in this wavelength and allows to detect a lot of high-resolution galaxies. And we also do the nearest parallel for this program. So in the right part, I show the example exposure from the top panel shows the NearCam imaging in the short wavelength channel, and the bottom panel shows the spectroscopy from the wide field slitless spectroscopy in the long wavelength channel. So this is the program design with JWST, but JWST is not the only story. This program, we have many common multi-wavelength observations to target this flux-limited sample. And for example, we have 100-hour ALMA band 6 Mosaic observation just approved in cycle 9. And we also have a lot of high-resolution observations for the quasar host galaxy itself. So basically, the resolution will match the NearCam resolution to study the quasar host galaxy in both stellar light and the dust and gas. We also have the radio observations and X-ray observations, and also extensive optical imaging from HST, and also ground-based optical imaging. So this multi-wavelength data set will really not only allow us to study the quasar and the quasar environment, but also study the galaxy evolution, cosmological organization, and the metal enrichment in the early universe. So next, I will move to the scientific results or early science results from this program. As I mentioned earlier, I will mostly focus on the large-scale environment of the earliest supermassive black holes in this talk. And for now, there are about half of the Aspire quasars has been observed by JWST, and I will show one case study of a luminous quasar at redshift 6.6, which already has multi-band HST imaging and the deep high-resolution ALMA observations. And then I will also briefly show some statistical results from the Aspire program. So let's look at the 6.6 quasar 0305. By looking at the NearCam slitless spectroscopy data directly, we identified about 4103 meters at redshift between 5.3 to 7. So this is a really large number of galaxies. Spectroscopically confirmed the high-resolution galaxies, and in the original, like the proposal state, we expect that we can only detect about 10 galaxies at its redshift range in single field, but we got 40. This is a huge difference. This is because the JWST is beyond our expectation, and also we found several galaxy overdensities in the fields, including one in the at the quasar redshift, as shown here. So this is a spatial distribution of those galaxies. You can see that all those different color highlighted circles are denotes to the high redshift 03 meters. You can see like they're distributed in the images, but it's like clustered in some way, like the red circles along this filament structure and the cyan points close to here, and there's no galaxy here, no galaxy here. So this plot already gives you a hint of galaxies are strongly clustered. And let's look at the redshift distribution of those 03 meters, as shown in the left panel here. Like the red one is galaxies at a redshift 6.6, like at the same redshift of quasars, and here shows the zoom in distribution of the line side velocity difference relative to the quasars. Like most of the galaxies are very close to the quasar, and which indicates the quasar does inhibit in a large-scale galaxy overdensity, and also there are some other galaxies are also concentrated to several redshift beams, especially for the redshift 5.4. You can see like there is a big galaxy access compared to other redshifts. So in the right panel, I show the a 3D plot of those galaxies. Like the red one is the galaxy overdensity traced by the quasar, and the blue one is the galaxy overdensity at redshift 5.4. So let's back to the spatial distribution of those galaxies. Look at as I previously mentioned, the red circles, which is the galaxies at the quasar redshift. So you can see most of the galaxies along this along this line or filamentary structure, and all these galaxies are within like very close to the quasar in the line of sight velocity, like the line of sight velocity within 1,000 kilometers per second also. So these are really physically related structure. And if you zoom in the center part of the quasar, so as shown in the right panel, we can see the brightest one is the quasar. The image is super sharp for the quasar itself. It looks like it's a composite of the 3 images. And in this zoom in figure, it's only about 60 physical kiloparsec times 60 kiloparsec. So this is a really small region, but we detect many galaxies in this region at redshift 6.6. You can see there is a quasar here. We have 3 C+ emitters identified from the ALMA. We have 2 O3 emitters identified from JWST. So those JWST detected galaxies are relatively young with strong O3 emission lines, but these C+ emitters are very dusty and more massive or heavily involved, especially for the C3 galaxy. It is even undetected in the JWST. So even undetected in JWST, it tells you that this is a super dusty galaxy. So this is a case study of this field. If we look at the more quasars, we might want to know all these galaxies or all quasars reside in galaxy over densities. Now, based on like half of the Aspire sample, we can already investigate this problem. So in the left panel, I show the redshift distribution of all O3 emitters identified in 14 Aspire quasar fields. You can see that there is clearly a galaxy number access at redshift between 6.5 and 6.8. This is the redshift range of our quasar. So by looking at this plot, you directly see there is a galaxy number access associated to the quasar, right? So in the right panel, I show the number of galaxies with the line of sight velocity within 1,000 kilometers per second relative to each quasar. Each bar represents one quasar field. So you can see that like many quasar fields has a number of galaxies more than 5. But in the blank field with a similar field view with a similar covered area, we only expect 1 galaxy within this velocity range. But like more than half of the quasar fields has more than 5. So which indicates more than half of the quasar reside in the galaxy overdensities. But there are some quasar fields with like the galaxy number density similar with blank field. So this also tells you like the quasar environment might be complicated. Like some of them may trace the galaxy overdensity, but some of them does not. So this is the early results. I wanted to leave my summary here and wanted to highlight that there, in this talk, I'm mostly starting the long-standing question of whether the earliest supermassive black hole reside in massive halos and trace galaxy overdensities. And these are really early results from our ASPIRE program. We will look forward to have more and more detailed studies of this question and to finally understand whether the earliest supermassive black hole reside in massive halos. And on Wednesday, Jin Yang will talk about the black hole growth and the aging feedback, as well as the black hole and galaxy coevolution using ASPIRE data. So I will stop here and would be happy to take any questions.
All right, I think we have time for one quick question. Yeah, Jonathan. We have the next speaker.
Hi, very nice talk. This is Jonathan Tan, Chalmers, University of Virginia. Do you have any evidence, either in the fields you've shown or generally, for any companion AGN relatively near a given high redshift AGN?
That's a good question. So we didn't find any AGN close to the quasar, but we do have some AGN candidates at a very low redshift, like detected the passing alpha line of some super broad passing alpha line of like indicates they are AGNs, but they are undetected in even HST images, so they are super dusty or obscured AGN. Yeah, but if with the, as I said, ASPIRE program has like X-ray and also radio observations. We are still trying to combine those multi-wavelength data to search more AGNs from this program.
All right, let's thank our speaker again. All right, so our next speaker is Guido Roberts-Borsano to tell us about first light, searching for and characterizing galaxies at the dawn of cosmic time.
Okay, thanks. Can you all hear me okay? Great, thank you. So I'd like to thank the organizers first for giving me the opportunity to come here and talk. And I realized today, exactly a year ago, I had booked a one-way ticket to French Guiana to try and witness, quite a spectacular event. And lo and behold, I gave the Hollywood performance of my life, worthy of a Nobel Prize, of an Oscar, and managed to see the launch live from the control room. So that was a very special event, and I think Christmas has really a lot to look up to this time. But so my talk is not about my limited career as an actor, but rather the first high redshift results coming from the GLASS ERS survey, led by Tommaso Treo at UCLA, and all these here at the bottom are our collaborators who have contributed to this work. So by high redshift, what am I referring to? I'm referring to galaxies at approximately redshifts of 8 or greater. The reason for that is they reside in a special epoch of the universe, dubbed the epoch of reionization, which is nicely put into context by this history of the universe over here. On the left, you can see that the universe started approximately 13.8 billion years ago with the Big Bang, and then expanded by inflation. And this expansion cooled it, and neutral hydrogen formed and essentially caused this fog, this cosmic fog in the universe, where the cosmic dark ages ensued. And after the first sort of couple hundred million years or so, the very first stars and the first galaxies formed and bathed the universe in ultraviolet light, thereby dissociating that hydrogen and rendering the universe transparent to UV light. And so studying galaxies at redshifts 8 and above or so is really important because it gives us constraints on when this process started, when it ended, and ultimately which ones were the culprits for this process. And so we've been pretty successful in, not changing slides, in selecting high redshift galaxies thanks to the so-called Lyman break technique. So as galaxies go to higher and higher redshifts, the neutral intergalactic medium absorbs their UV photons, and so you get this very characteristic break over here. And by strategically placing photometric filters, you can locate the approximate location of that Lyman break, which serves as a proxy for the distance of the galaxy. And so deep fields and lensing clusters, this is a very outdated plot now, but I think highlights or will highlight the progress that we've made, gives us a lot of galaxies at lower redshifts of 6 and 7 or so. But as galaxies get redshifted to infrared wavelengths and become dimmer and dimmer because of their their fading brightness, we need filters in the infrared to characterize the location of their Lyman break, as well as the rest frame optical of this galaxies, which is where most of the stellar mass and emission lines from stars is found. Ultimately, of course, we want to spectroscopically confirm these galaxies to get a precise measurement of their distances, but this is very tricky from the ground, purely because, well, for one of the reasons that the atmosphere blocks a lot of infrared light, and so you really only have some very specific windows where you can try and target bright emission lines. And at redshifts greater than 7 or so, one of the most bright emission lines that you can get is Lyman alpha, except that Lyman alpha, being an energetic line at redshifts greater than 7, where the universe is highly neutral, gets attenuated. So this, I think, showcases really nicely how Hubble has been a fantastic servant for us up until now, but James Webb really is the one that's going to be pushing to higher and higher redshifts. And so the GLASS-ERS survey has two main aims. One of them is to characterize galaxies at the earliest of times, and the second one is to try and understand how baryons cycled through galaxies from redshift 0 to higher and higher redshifts as well. And so it targets the Hubble Frontier Field Galaxy Cluster over here, Abell 2744. The GLASS-ERS survey is the deepest of the extragalactic ERS surveys, with 35 hours approximately of observation times. And so it's going to try and characterize, or it is characterizing, this beautiful cluster over here. And just in this HST image, you can see the plethora of galaxy types that we have in here. We have low redshift galaxies, high redshift galaxies, merging galaxies, singular starbursty galaxies, all different types. And crucially, and this is a very unique aspect of this program, is that we make use of nature's magnifying glass. And what I mean by that is that these massive cluster galaxies in the foreground, the extreme gravitational pull from them bends and amplifies the light from background galaxies. And so we're able to find galaxies which are so faint that otherwise they would have been missed in deep fields. So we have three different modes. The first one is with nearest wide field slitless spectroscopy over the center of the cluster in 3 different filters and 2 different orthogonal directions. And so what that gives you is a spectrum from about 0.8 microns to 2.2 microns for every single object within that field of view over 3 filters. So you're covering, for high redshift galaxies anyways, pretty much a large range in wavelength to characterize the Lyman break and emission lines. At the same time, in parallel, we are observing 2 different pointings with NearCam, 7 different filters over here. These are very deep images. This is a nice RGB image from a NASA press release. And so these filters over here allow us, the infrared coverage that we need to try and look for galaxies at redshifts greater than 9 or so via the location of their Lyman break. And then finally, for dedicated targets or specific targets within this field, we follow them up with NearSpec, where we have very high resolution, so R of 2700 over hundreds of galaxies and objects within this field of view. So the first data arrived July 15th. On July 19th, we put out our first paper where we did a search in the NearCam fields to look for very, very high redshift galaxies. We predicted we'd find 0.1 galaxies in our field, and we found 2. So these are those 2 candidates over here. You can see they're very clearly detected in the bands redward of the Lyman break, in both cases over here. You can see that they have a very strong break as well, nearly 2 magnitudes, which suggests that these UV photons are being absorbed. And crucially, they also have flat or very blue slopes. This is very difficult to explain if the galaxy is a low redshift interloper. So a galaxy at low redshift that's masquerading as a high redshift galaxy. And what I really like to point out is that if you were to try and observe these with Hubble, over here you might find this galaxy over here with this filter, but this galaxy would be completely missed by Hubble. So you really need James Webb to find that. So are these galaxies completely unexpected? Well, I told you the prediction was 0.1 galaxies, and we found 2, so something's a little bit weird over there. But if we plot the luminosity function over here, which Steve nicely highlighted before, there are 3 different models where you have a star formation efficiency, which is tied to your dark matter halo mass, with some dust, with no dust, and also an extreme model where you're converting all of your baryons into stars. And you can see that whilst the error bars are quite large over here, the models are consistent with galaxies forming at these early times as long as there's very little to no dust. And this is a nice example of the Redshift 12 luminosity function here, where several other authors picked up the same objects and found a few others as well. And so this is consistent with previous HST determinations of these galaxies. However, the real trick is to try and spectroscopically confirm these sources because, as you know, without the spectroscopy, you don't know whether they're low redshift interlopers or actually high redshift galaxies. So we teamed up with our friends in Japan, Tom Bax and Jorge Zavala. We had 4 hours on source in band 6 of that brightest of the 2 objects, and we found a 5.5 sigma emission line. This is O3 at 88 microns. And you can see it relative to the source here. This is where the line is relative to the source. So there's a little bit of an offset, which is not immediately clear to us. So we're a little cautious in claiming, some huge detection. But the redshift of the line, 12.11, is in perfect agreement with the photometric redshift of that very distant galaxy. So this is a very metal poor and a very dust poor galaxy. But it's tricky because if its metals are so low, we can't really get the line. So the next best thing is to try and get the Lyman break directly, which we did with NearCam. None of these objects, but some redshift 8 objects within a field. We have a tentative protocluster of galaxies over here. And with NearCam, you can see that we pick out this Lyman break very, very clearly for 2 of the objects highlighted in pink over here. And you can clearly see their Lyman break at about 1.1 microns, which gives a redshift of about 8. Now, when I talk to the PI, Tommaso Treo, and say, look, we need to follow up some of these Redshift 8 objects. At this point, he goes, well, Guido, Redshift 8 was so 4 months ago. So these are very bright galaxies, of course, and it's very useful to use NearCam over the wide field slit list, where you're not targeting a specific galaxy, but you're getting everything in the field of view. But we can do this with NearSpec as well, because we can only target the very brightest ones with NearCam. And with NearSpec, we set out to confirm the other galaxy, Redshift 8 galaxies within that protocluster. So there were 6 other ones where we put a micro shutter slit on top. We got 100% confirmation rate with those galaxies, looking at O3 over here that you can see, and H beta, and over here is the Lyman break. So one of these is with Prism, and the other over here is very high resolution R of 2700. So it's pretty incredible. These galaxies, we've been waiting forever to try and confirm them. And with 1 or 2 pointings with NearSpec, we get those galaxies. And we can, because these galaxies are lensed, we can use our model of the gravitational lens to reconstruct them in the source plane and find that they are only separated by about 50 to 60 kiloparsecs or so. We can put some of the first constraints on the halo mass of this potential protocluster from the 6 spectroscopically confirmed objects, and the velocity dispersion under some assumptions of this protocluster, finding it to be about 1,200 kilometers per second or so. And finally, the last result that I want to present we got a DDT proposal approved to follow up some objects within this cluster field, and of particular interest is this galaxy here, JD1, which was identified as a Redshift 10 or so galaxy with HST. Adi Zitrin et al. Had found this, and you can see it's a triply imaged galaxy. So 3 postage stamps here from using images from the Uncover survey, and you can see their positions here relative to the big galaxy cluster over here. And we targeted the brightest component, component B of this, with NearSpec Prism, and we got a very nice spectrum out of this, confirming the galaxy as a Redshift 10 or so galaxy, specifically at a redshift of 9.79. You can very clearly see the Lyman break here at about 1.3 microns, and very tentative emission lines here, peak signal to noises of about 4.5 sigma. This is hydrogen gamma, nitrogen 3, and hydrogen beta. And so to date, because this galaxy is amplified by a factor of 13 or so, if you correct for this amplification, this galaxy is currently the faintest galaxy that we know of in the early universe. So about a month ago or so, James Webb finally gave us our first gaze into the dark ages. And really, I think, sets the benchmark for what's to come with the next programs. And lastly, because of this gravitational lensing, we can use our model and the detailed images which resolve individual components over here to reconstruct the galaxy in the source plane before it is amplified into this very compact object over here. But I think I'm out of time. I'm going to leave with my summary and conclusions. The first is that with the GLASS ERS survey, we've been able to find a new set of luminous galaxies at redshift greater than 10 when the universe was only about 500 megayears or so. With NearCam, NIRISS, and NearSpec follow-up of these galaxies, there's a very high success rate, either from the Lyman break or from strong emission lines in the rest frame optical. With those, we managed to confirm the most distant protocluster we currently know of at a redshift of 8. And finally, the combination of NearSpec and NearCam confirm this dark age galaxy and is able to reconstruct its morphology into its pre-lensing condition. So thank you.
Okay, we have time for a question or two. One over there. Actually, 2, yeah.
I can't hear you.
Okay. So very interesting stuff, and my ears sort of pricked up when you said that high redshift is now redshift greater than 8, and that's the epoch of reionization. Because at any conference on reionization from about 2011 to 2021, I would have expected someone to say 7 there. Now I'm also kind of pleased because it actually matches what we've been finding in the Logger survey, where we're finding redshift 7 galaxies from Lyman alpha and finding no apparent decline in their luminosity function that exceeds what we're seeing in what's seen in the UV continuum luminosity function. So that's recent work by Wald et al. And I want to just
have more than 90 minutes today, so we get started.
So
welcome again.
Anyway,
please mute online.
Live. Hello, everyone.
So with the protocluster that you were finding, I was curious there, do you have a sort of a mass estimate for that object?
So we managed to put a lower limit on the halo mass of, I think it was 4 times 10 to the 11 solar masses or so. Obviously, it's a little difficult to say given, there are certain assumptions that go into that. For instance, this I would claim is a candidate protocluster. So we think this is a protocluster that would eventually form a massive cluster like we see low redshift, but, that's an assumption at this point. So yes, we do place a lower limit on that estimate. Because there are some other galaxies, of course, that are still photometric candidates. And so if we confirm those, that number might change.
Good. This is Feng Wu from University of Arizona. So for the Redshift 12 candidate you show, there's almost line detection, 5 sigma. But if I recall correctly, that's a telluric absorption feature frequency at that exactly that frequency. Have we all group or take that into account?
Sorry, you're saying that's an
So
absorption
for that
frequency?
frequency, the atmosphere transmission that's a deep. So the spectrum should be much more noisy at that frequency, and that may produce artificial lines. Have you group ever looked at this interpretation?
So I haven't dealt with the data directly. There's been Tom Bax, but they have been doing a lot of testing with the data to make sure that this is not some chance event or a noise event, for instance, checking whether there are other peaks in the spectrum that might resemble that. But it seems like a fairly unique event within the spectrum that we have. Our biggest concern really is that it seems to be slightly offset to the northeast, about 0.5 arc seconds, and that it's very wide. But I don't think we have any reason to be worried about it being some spurious event at this point.
Okay, thank you.
All right, there's one question online, if we can do it really quickly.
So Paolo Andriani has asked, which models were you talking about predicting 0.1 galaxies?
Those were models by the Rome team that analyzed the NearCam images, so Adriano Fontana and Marco Castellano, and they use their simulator. It's called the egg simulator, empirical galaxy something. I can't remember the exact name, but essentially that's based on luminosity functions, if I remember correctly, from the GOOD survey, and you can get predictions from that. Okay.
Thanks. Thank you, speaker again. All right, so our next speaker and the final one of this session is Dan Coe, who will talk to us about the early history of distant galaxies and the lens star Earendel.
All right, thank you very much. Hope you all can hear me. So exciting to be here. Welcome everybody. We're doing it. JWST Science after all these years. So thanks to you all and folks online. Thanks to the organizers, and thanks to, as Jane Rigby mentioned, she counted them. 20,000 people have worked to make this possible over decades. So thank you so much for delivering this incredible machine and all the work you're continuing to do. So when I first saw this image, I was blown away, as I'm sure you all were, especially when you compare to our Hubble image that we took as part of the RELIX program. And you flip back and forth, you can see so much more detail. And when you zoom in, you see all these tiny structures, globular clusters, as we mentioned. And then this galaxy in particular, if I can get it here, caught my eye, and among other people. And you're seeing all these tiny clumps that you were never able to see before. This is the Hubble image for comparison. And these little clumps, each one of these little clumps is like 30th magnitude at 1 micron. So Hubble is going to have a really hard time seeing that in any but the deepest images. And it gets a little brighter, so 28th magnitude at the rather wavelength. So that's how JWST is able to pick it up. And so I thought we are witnessing cosmic spring here. So these tiny, whoops, a little delay on that. These tiny buds of star formation in the early universe and galaxies that look very different than most of the galaxies we see, spirals and ellipticals, around us today. Well, it turns out I was wrong about this for a couple of reasons. So first of all, we don't need a cosmic spring. We already have a cosmic dawn and a cosmic noon, so we don't need to bring seasons into this. And also, it turns out these aren't young buds of star formation at all. These are actually very old, it turns out. A couple of papers looked at this. They found that these are actually globular clusters. So billions of years old, already in place. This is being observed at Redshift 1.4, 9 billion years ago. These were probably already in place a billion years or so after the Big Bang. And so these are where globular clusters form. We've known that they're old, and so we're seeing them already in place many billions of years ago. And so this brings us to my programs. I kept the name Cosmic Spring, but these are two other galaxy clusters that we observed. We have the imaging already. We're very fortunate with the scheduling, but we don't quite have the spectroscopy. We'll be getting that later this month, and then also in early January, so both in time for Cycle 2 proposals. I made all this data public, which I'm happy to do here. We have a lot of resources. I know it's not the same for everyone, but all of this is public. You can go to our website and get the data, analysis tools, color images. There's also blank fields, by the way, off to the side. And thanks to an amazing team, and just privileged to be working with all of you. And we might even create a few more members from this conference if people are interested. Yeah, they've been teaching me a lot about galaxies and stars and that kind of thing. And so 5 papers we have so far. I'll try to race through them and show off some of the work that our folks have been doing on this. And plus a paper in PrEP led by our postdoc Abdurraf, looking at resolved stellar properties of galaxies out to Redshift 6. So similar to the clumps analysis, this is just looking at regions within galaxies and mapping their properties from the center out to the core. And for the most detailed look at a galaxy in the first billion years, this is the Sunrise Arc. This is work led by my former grad student, Brian Welch, when he was here at Hopkins. He's now with Jane Rigby at NASA Goddard. And so this is the Hubble image. And we now are looking at it with JWST, and we see a lot more detail. I'll flip back and forth there a little bit. And you see some of these star clusters light up in O3 emission that we can see just in the imaging. So we're getting the spectroscopy later this month, but with NearCam, you can see these really bright lines, O3 and also H alpha. And you can map them out in the exquisite detail that NearCam offers. And you can see it here in the spectra that Gaurav Kuller did with the SCD fitting with Prospector. Adelaide Claessens and Angelo Adamo fit these other clumps that don't quite light up with this emission. These are a little bit older, and so these are bound star clusters, gravitationally bound, that we're seeing 13 billion years ago. So these are the precursors to the globular clusters that I showed earlier. So we think these were already in place, 13 billion years ago, just a billion years after the Big Bang. And by the way, just a parsec in radius. So these are extremely small clusters we're able to see in this very distant galaxy. And so this is also host to the lens star Arendelle. So this is work that Brian did also when he was a grad student here. JWST was designed to study the first stars. And a lot of us thought, well, that we mean, star clusters within the first stars, or maybe if we're lucky, we'll see a supernova. We actually found with Hubble an individual star or star system that we could see, 13 billion years ago and study in detail with JWST. So you saw what the images looked like, and from the colors, just from the colors alone, we're starting to figure out the spectral type. Might be a B star, or we might see hints of 2 stars here, an O and B star. So these are hot stars. They're very luminous. Like I said, we're going to be getting the spectra, and we're putting them on the HR diagram. So this is what we had with Hubble, these constraints. And now we're down to this. And this is my cheat sheet over here. I don't normally work on stars, but we're up in this region up here, the supergiants. In fact, we're up off the charts. This is 60 solar masses. This is going up to hundreds of solar masses. So these are definitely massive stars. And the folks who work on stars tell me that they don't quite know how these tracks work in detail. These stellar evolution tracks, especially at a low metallicity, which we don't know yet. But Arendelle might be low metallicity, being in the early universe. And we'll find out with these spectra that we're getting, and see what stage of evolution they're at. Stars have been discovered in the Hubble frontier fields. You take these ultra-deep images combined with lensing, and there were stars discovered at Redshift 1. Well, every time you observe with JWST, you basically get a Hubble deep field. So we're now seeing these stars pretty much all the time we look at a cluster. This is the other cluster we observed. We see a Redshift 5 star candidate. Right here on the lensing critical curve, like Arendelle, you see the symmetry from the lensing for the other star clusters, and this one is right in this high magnification region, work led by Ashish Meena. And this is probably a B star, so another very luminous, hot star. Not super hot, but hot. And we're going to get these spectra that we expect the spectrum to look something like this out later this month. And so we think we've kind of ruled out these hotter stars, but it might be one of these cooler ones around 10,000, 15,000. These spectra here. If it were a galaxy clump, a star cluster, we might see these nebular emission lines. And just let's take a step back, just talk about how amazing this spectroscopy is. For any of you who've worked on this, this is work by, people like Taylor Hutchison, Rebecca Larson, Inte Zhang, Steve, a bunch of people. You've all been working on this, and you're lucky to get one line with really hard work, lots of time on Keck, Mossfire, for example. And now, We have a lot of advantages, and you all saw the ERO spectra, 10 lines at Redshift 8.5, and they're booming, and they pop out. And this is just some of the very first data. We also see this kind of thing in the imaging. There's been a lot of different papers on this. This is one of ours from Larry Bradley showing, booming O3 emission plus H beta. That again, you can just map out with the imaging. If you're interested in O3 or H alpha at lower redshift, that you just see it in the imaging. Some have it and some don't. So now we're getting to the population statistics. How many galaxies are intensely star forming and could probably help reionize the universe versus some that are a little bit more calm and are still actively star forming, but maybe not as intense. And this is one of my favorite results. This is from our other program. I discovered this galaxy 10 years ago with Hubble. I've waited 10 years to look at this galaxy with JWST. It's one of the most distant known with Hubble, maybe third or fourth. Very small galaxy. This is an entire galaxy the size of a giant molecular cloud in our own galaxy, or M74, for example. 100 parsecs or less. As Carl Sagan might say, we're going to look again at that dot. He'd be most interested in the exoplanet results, but he might be interested in this kind of thing too. And so we took a look, and we actually saw 2 dots. And this is work led by my grad student. He's here, Tiger Xiao. He has a poster here. Make sure you get to talk to him. So we see very tiny clumps, different colors, and 20 parsecs in radius, 70 parsecs in radius. These are the real building blocks of all the galaxies yet to come in the universe. And there's a companion. So a few kiloparsecs away, there's another companion, similar redshift. And when we delens things, very striking resemblance to a simulation by Kirk Barrow. He wasn't trying to simulate this galaxy. This was just from his simulation. And there's if you look in the gas, there's a bridge connecting these. These are getting ready to merge. So this is the story of how galaxies like our Milky Way came to be. And again, we're going to get spectra. This was from the proposal. NearSpec is more sensitive now. This galaxy is also brighter. It's like twice as bright. We weren't going into such long wavelengths. So this is a plot from Tiger's paper just showing, this is one of the brightest galaxies known. It's significantly brighter than other, more recent galaxies discovered at these redshifts. So we can get a lot of detail, and we're going to show you what lines we see in time for your Cycle 2 proposals. Again, it's all public. And if we redshift that ERO spectrum a bit to higher redshifts, I'm hoping we might see a bunch of these lines, maybe, a little more optimistic than what I had here. We're using the Prism, so some of these will be blended, and we'll have to come back with MIRI in another cycle, hopefully, to get O3 and H alpha. But very exciting. And if you think Redshift 11 is so, 3 months ago, we also have higher Redshift candidates I think, by the way, lower intermediate Redshift 6 to 8. That's where there's so much science there. But if you want to push it to higher redshifts, Kadus Worku, our grad student, has been looking at some of these candidates. We're going to get spectra of both of these too. So we'll see what we can confirm out to higher redshifts. This is just a small portion we've been able to cover in this section. We count 150 papers so far in galaxies, predominantly led by men, and including within our own team, by the way. And so we have to figure out what we're doing wrong. One of my colleagues suggested, give a little more time for people to volunteer to lead those papers or lead those proposals. Your team might be doing that, but maybe there's other things we can do. I know the high redshift community has come a long way. There's still more work we can do, and especially for the younger folks, getting you involved, students and postdocs. This is going to help launch your careers, and it's such an exciting time to be doing this. So I hope you're enjoying it as much as we are. So thank you.
All right, so time for a couple of questions. Of course, it is all that separates us from coffee, so...
Plenty more time.
Yeah. Any questions for Dan? Yeah, go ahead.
Hi, Dan. I just want to ask a ETC question for your Redshift 11 very bright galaxy. How long do you think MIRI will get to O3?
With MIRI, oh, good. By the way, I should have mentioned with NearSpec, we're going to do 4 hours. But yeah, we could obviously go deeper. MIRI, I think we can do that in a small program. I think, yeah, we were looking at it last year, and I think Tiger's looking at it again this year. He'll lead the proposal. But, 4, 6, 8 hours. It's more sensitive now, though, so I know I haven't checked with the latest. And it depends a lot on, what type of galaxy, what parameters it has, but certainly doable. In a small program, I think. We'll find out.
Okay, thank you. Very amazing.
Yeah, and I should mention this is 25th magnitude. Yeah, so the ones Emma was showing, for example, I think are more like 29th. And so we're going to see what it takes. If this is this bright and you're looking at a galaxy that's 28th, how much exposure time would you need for that one instead? Yeah.
We have one question over here.
Hello, I'm Divakara from Mexico. My question is, how sure are you that those are stars, not clusters? I mean, you have some uncertainty of lensing parameters and all, no? Given that.
Yeah, that's a great question. We're fairly confident, but that's why we're going to get the spectra and see and try to distinguish it from the having these nebular components, for example. But it's this one is a newer one, and there might be another one actually in this galaxy. Arendelle is, it all kind of hangs together with the right luminosity and the colors. But yeah, it's right on that lensing critical curve. So it's hard to figure out what else it could be. But yeah, we're about to find out. Yeah.
Thank you.
Okay, then I suggest that we thank all of them and all our speakers again.
One quick announcement. I want to remind you all that all the posters are up on Slack or also viewable through those screens that are in the cafe. So please take a moment to look at them. I think there's more than 40 posters, and there's loads of people online who would love to converse with you about them. So take a moment and do that. That's it. Enjoy your coffee.
All right, thanks. Oh, if you want, yeah, absolutely. I think we're not sharing anymore. Just go ahead. Cool. Okay. Sorry. Don't unsee it once you've seen it. Cool.
I blame my cats.
So good. Okay. Cool. Thanks.
Got Imca's latest. Yep. You've written me. Hi, I'm Chris Evans. Heard a lot about you from Emily. Sounds like good things with your paper. Yeah, there were a few versions, so it'd be good to. I guess. No, I'm doing exactly this. So I don't know if it was. So if you upload a second one, it adds the date stamp. So this was probably. Did you just do one update, or is there a couple?
I did two later because I don't like the colors.
Okay,
so
cool.
Okay.
Oh no, that's cool. Let's see.
You would have noticed. Is your office open, by the way?
Yes.
Okay. So if you kind of transfer my stuff,
Cool. Yeah. Yeah. So the latest. The latest one in box is from the 8th of December. So there was like an original one, then an updated one, which is this one. Then you can see if this looks like the one that you're expecting. If not, we can do another upload.
It looks good. I just don't have a date on it. That's probably the.
You can edit it direct if you want. Like,
oh, okay, cool. Thank you. It's the 14th, right? Yeah.
Yeah. Cool.
That's cut off, yeah. Okay. Wait, what'd I do?
Dropped off the bottom. It just dropped off the bottom of the.
Yeah.
Yeah, when I first saw the Galaxy, I thought it was that like just walking around.
It's fine. Okay. OMG, dude. Okay. Sorry about this.
No, it's cool. Those things are set in your mind.
Okay, I'm gonna just have to live with it.
Works.
All right, this is the one. So should I delete the other ones, or what would you like me to do?
Yeah, you happy running it off PowerPoint rather than the PDF?
Yeah, I didn't know what you all preferred.
Cool. That's fine. So if we'll get rid of those two, and then say goodbye to that one, and then we're good.
Okay, and then. Nice. Okay. Easy peasy.
Awesome.
Thank you.
Thank you. Session 3. Who have we got first? All right. Either.
I just have to. I hope Thank you so much. That's okay. Sorry.
Oh, that's very Oh, really good.
Yep. Hard, right? Yeah.
Oh, that's great and sobering all at the same time.
Yeah.
Your grand students, yes. Well, I'm sure it is my first one. Well, summer in Stockholm. Oh, it's terrific. Cool. I've seen it watching. That comes right at the right. I was going to say, yeah. Twice as much. Yeah, I mean, this is obviously a lot. Oh, all right. Yeah. Good. Yeah.